Okay, so this afternoon we'll have two talks for our AGEA Zoom seminar. So first talk is given by Professor Gu Yi from Suzhou University. He will talk about the surface fabrications with large equivalent automorphism groups. Okay, please.
Okay, thanks organizers for invitation. And today I'm going to talk about the equivalent automorphism groups for surface vibrations. So let me start now. My talk will be in 5 parts. And first, let me talk about the equivalent automorphism group. And it is known that automorphism groups of algebraic varieties is one of the central topic we study in algebraic geometry. For example, in this afternoon, the 2 talks are both related to automorphism groups. And in fact, we will meet various automorphism groups in our studies. And let us first fix an algebraic closed field K. And we will usually study the following 3 kind of automorphism groups. First, we study the automorphism group of K variety, which I think I call it the absolute case. And in some other cases, given a morphism from X to Y, we will also study the relative automorphism group, which is the automorphism of X, so that F sigma is equal to F. And also we have some birational version of the automorphism of X and the birational relative automorphism group. In this talk, we will focus on another relative version of the automorphism group. This is called the equivalent automorphism group. Its definition is like this. Suppose we are given a morphism F from X to Y. Both are K varieties or K schemes. Then the equivalent automorphism group is defined as follows. It consists of the pairs tau and sigma, where tau is an automorphism of X and sigma is an automorphism of Y, so that the F sigma equals to tau F. Roughly speaking, this is a pair of automorphisms of X and Y that preserves this morphism structure. And this set admits a natural group structure. This is, we call it the equivalent automorphism group. And I will use this EX over Y to denote this group. And let's first talk about the basic structures of the equivalent automorphism groups. For example, we know the representability of this group. If both X and Y are projective K varieties, then this automorphism group is in fact represented by a closed subgroup scheme and denoted by still EX over Y, contained in the product of automorphism of X and the automorphism of Y. And in this case, this abstract equivalent automorphism group is the key point of this group scheme. And if X and Y are smooth, we can even work out the Lie algebra of this group scheme. It is a direct sum of the global section of Tx and the global section of Ty over this group H0 F pullback Ty. Here Tx and Ty are the tangent bundle of X and Y, and we have natural morphisms from global section of Tx to the global section of F pullback Ty and H0 of Ty to its pullback. And the Lie algebra is like this. But it should be noted that in positive characteristics, this the Lie algebra is at the dimension of the Lie algebra is at least the dimension of the group scheme, but the equality is not always the case. So sometimes you will have very large Lie algebra, but the group may be very small. Then from the construction, this equivalent automorphism group EX over Y admits natural projections to X and to the automorphism group of X and that of Y. So I will denote by F upper sharp and F lower sharp. It maps the pair tau sigma in this equivariant automorphism group to tau and sigma respectively. Let's first concentrate on this F lower sharp. The code of this F lower sharp by definition is nothing but the relative automorphism group, which is denoted by this node automorphism y x over y. And as such, we will have the following left exact sequence. From this sequence, we define usually this F lower sharp is not surjective, and by this we define the B automorphism group as the image of this F lower sharp. In my opinion, this group deserves a specific name, but I didn't find it in literature. So if any one of you know this, please let me know. So at the moment, let's call it B automorphism group. It is the image of this equivariant automorphism to the automorphism group of Y. And with this notion, we have a short exact sequence of groups. The left side is the relative automorphism group, and the middle is the equivariant automorphism group, and the right-hand side is the B automorphism group. And also we can also find that the another projection, the F upper sharp homomorphism, is also has some nice properties. And usually this F upper sharp is an isomorphism. In fact, for many morphisms, if this morphism is defined from some geometric settings, then this F upper sharp will be an isomorphism. For example, if F is an Arbanese map, or it's a pluricanonical map, Itaka fibration, or anti-pluricanonical maps, and some other canonical ones like this, they are all for these maps. F upper sharp is an isomorphism. Also, there is another setting that if X is a hypersurface and F is embedding to the ambient projected space, then this F upper sharp is also an isomorphism. But there are also a few exceptions. Usually, this F upper sharp is an isomorphism in case that F is somehow natural. And I will also introduce the equivariant automorphism group with some extra conditions. So suppose this morphism F from X to Y admits another algebraic structure, then we will also consider the equivariant automorphism subgroup that preserves this algebraic structure. For example, in this talk, I will use equivariant torsor automorphism groups. In this case, let's suppose this morphism pi from X to Y is not only a morphism, but it is a torsor on the group scheme G. Then this time we define the torsor equivariant automorphism group, which is a subgroup of this equivariant automorphism group, consisting of the pairs, so that the G action on X is preserved. That means the tau in this pair tau sigma should preserve this G action. In other words, this diagram is commutative. Here, mu is the G action on X. And similarly, we can define this B torsor automorphism, B torsor equivariant automorphism group, which is the image of this E torsor automorphism group. And okay, I use this E tau X over Y to denote this equivariant torsor automorphism group, and similarly call this B tau X over Y. With this example, we have defined these two groups, but to be familiar with this group, let's check an easy example. Suppose this time pi X to Y is in the Galois cover with Galois group G. Under this setting, X is naturally identified as G torsor over Y, and we can work out this E x over y and E tau x over y. In fact, this pi upsharp embeds E x over y to the automorphism of x. And its image is exactly the normalizer of this G in this automorphism group of X. And at the same time, this E tau X over Y is identified with the centralizer subgroup of this G in this automorphism group of X. So this is a kind of equivalent automorphism groups. Then let me introduce some works related to the equivalent automorphism groups. So as I mentioned, usually if this morphism fx2y is defined from geometry, then the F upper shaft identifies the equivalent automorphism group with the automorphism group of X. So usually people will study the automorphism of X in an equivalent point of view when it admits automorphism F. So when studying this group, we identify it with the equivalent automorphism group and using the, for example, the short exact sequence we introduced to study this group. And over C, for surface X, we have also some interesting results. In 2015, Hu, Kim, and Zhang introduced some results. They gave some dynamic criterion so that given a subgroup G in the automorphism group X, you can determine whether this G can be embedded into some equivalent automorphism group for a suitable fibration F. And more recently, Prokhorov and Sharamov, they studied this group B automorphism group for some natural surface fibrations. And they find that the fineness of this B automorphism group is related to the Jordan property or the bounded finite subproperty for the automorphism group of X or the birational group of X. And this is in fact the motivation of this work. So we, in literature, this group B X over, in this case is a surface fibration. This group is not well studied, and I want to know more about this group. And also I want to learn how this group is related to the Jordan property or the bounded finite subgroup property of automorphism of X. So we will focus on equivalent automorphism group for relatively minimal surface fibrations. So we will discuss the equivalent automorphism group for F with the following settings. So we assume F is a relative minimal surface fibration of an algebraic closed field K of arbitrary characteristic. This means X is a smooth projective surface of K and C is a smooth projective curve. And F is a flat morphism with geometrically integral general fibers. And there's no vertical -1 curves. And we will pose another non-trivial condition. We assume the general fiber of F is smooth. This condition is true in characteristic 0 for the Bettini theorem. But as we know that in positive characteristics, we have fibrations with singular general fibers. For example, the celebrated quasi-elliptic fibrations. In this talk, I will not. I will later at the moment. Let's assume we do not consider such fibrations. So we assume the general fiber of F is smooth, and this will bring. In fact, the singular general fibers will be.
没有，我站一会儿我就出去晒太阳，妈的。
And our aim, and the aim, and the main target of this talk is to answer the following question. So we want to determine whether this group equal EX and the base automorphic group EX over C. We want to determine that these groups, whether these groups are finite or not, and whether they are finitely generated or not. So this is the main question we want to answer in this case, in this talk. To do this question, I will introduce an equivalence relation on groups. We denote by this equivalence symbol to denote the equivalence relation on groups generated by the following relation. So the relation is like this: G and H are related, are equivalent if there is a homomorphism, so that the kernel and kernel are both finite. It is a classical exercise in group theory that the finite finitely generated property is preserved by this equivalence relation. If G is then H is also finitely generated. Okay, now let's turn to the this question, and let's first take a baby case. Let's first study the equivalent automorphism groups for fibration of genus 0. As we assume that the fibration is relatively minimal, so if fx2c is a genus 0 fibration, then X is a projective bundle of a rank 2 locally free sheaf E on the C. And we can now use this locally free sheaf E to interpret the three groups we are studying. I will not go to details. They can describe clearly. And by this description, we can find that the subgroup, we can find that the relative automorphism group of X is in fact equivalent to this group, the automorphism of this sheaf modulo the K star action. And as a result, we can find that this automorphism, relative automorphism group is finite if and only if this sheaf E is simple. Otherwise, if E is not simple, then this group is never finitely generated. This is the result. Sorry. And in case of the base automorphism group, if the by definition the base automorphism group is a subgroup of the C. So if the genus of C is at least 2, then it must be finite. There's nothing to say in this case. And if the genus of C is 0, then we can see this the automorphism group is never finitely generated, actually. And when it comes to the genus group can not finitely generated. In fact, at least over C, you can use of to mean are not finitely generated. So the complete is also, and finally, in summary, we can find that this equivalent automorphism group can be either finite or not finitely generated. So this is a case of genus 0. You can reduce the question to the automorphism group of a vector bundle, and everything follows quite trivially. Now let's consider the relative automorphism group for vibrations of positive genus. In this case, the relative since we assume F is a minimal, since F is relatively minimal, so the minimal model theory tells us that the automorphism of X is in fact equal to the automorphism of the generic fiber over the generic point. Here, K is the function field of C and eta is the generic point. So the automorphism of X over, so the relative automorphism of X over C is equal to the automorphism group of X eta over K. And it can inband to the geometric static. And as we all know, the automorphism group of genus at least 2 curves are finite. So if G is at least 2, then this group must be finite. And in case of genus 1, when you have a genus 1 fibration, you will associate a Jacobi fibration, which I will discuss, I will introduce later. And we can use this the Jacobi fibration to determine whether this group is finite or not. In fact, this group is finite if and only if the group of sections, this JC is the group of sections for this Jacobi fibration. So the relative automorphism group is finite if and only if this group is finite in case of G equal to 1. And this group is not finitely generated. This automorphism group is relative automorphism group is not finitely generated if and only if the Jacobi fibration is not is trivial, still in the case of G equal to 1. Okay, I will quickly. Okay, let's first recall the Jacobi fibration of a genus 1 fibration. Suppose F is a genus 1 fibration, then the genetic fiber X eta is a smooth geometrically connected curve of genus 1. This curve is not necessarily an elliptic curve. It may not necessarily have a rational point. So it do not have a group structure, but we can associate a elliptic curve, which is, by definition is pk 0 of this X eta. Then this J eta will be elliptic curve. It has a natural group structure, and this J eta is called the Jacobian of X eta. And the Jacobi fibration of genus 1 fibration is nothing but the main model of this J eta over C. So observing that this generic fiber X eta is a genus 1 curve, so it is naturally identified with the pk1 of itself. The point on itself classifies the degree 1 line bundles on it. So as a result, this X eta is a torsor under this J eta. So in fact, you have the pk group, and the J eta is nothing but the identical component of the pk group, and the X eta is another irreducible component. So this X eta admits a natural torsor structure under this J eta. And in fact, it's an ideal torsor. It's well known that torsors under this group scheme J eta is classified by the first dark homology, and we can use we denote by this O X eta to be the element associated to this X eta. It is not difficult to see that n times this group is abelian, so this is an abelian group, and n times if you take a positive integer n times this O X eta, you will get another element, and this element in fact is associated to the torsor pk n X eta. In particular, if you have a invertible sheaf of degree n on X eta, then you have a rational point in on this torsor. So in particular, this torsor is trivial. Namely, this n times this O X eta will be 0 if there is an invertible sheaf of degree n on this X eta. So roughly speaking, when you have a genus 1 fibration, the genetic fiber X eta is a torsor under its Jacobi fibration, and this torsor is represented by a torsion element in the H1 J eta. And in fact, this formulation of torsor structure is in fact defined not only at the generic point, but over the smooth locus U of this F, and by the theory of pk function due to Golden-Dick and others. So now we can give a brief proof of the theorem 3.1 in case G equal to 1. So we want to understand this group automorphism X over C, and this is equal to the X eta over K. And this automorphism group will naturally induce an automorphism on the Jacobian. So there is a natural homomorphism. The kernel of this kernel of this homomorphism is nothing but the key point of this J eta, which is also equal to the JC. As we know, this group is finite. The right hand side, this group is finite. It's a group homomorphism of an elliptic curve. This is always finite. So this automorphism group is equivalent to the section group of its Jacobi. So it's finite if and only if this is finite. Next, later we consider the trace. We identify this notion, the KK trace of this Jacobi J eta. Then we have a natural exact sequence. The small k point of this trace embeds to the big K point of this J eta, and we have the quotient. The celebrated theorem of Lam-Nehong says that the right-hand side is finitely generated. So if this group is not finitely generated, then this group must be non-trivial. But it's an easy fact that this group is non-trivial if and only if the Jacobi fibration is trivial. So in all, we show that this group is infinite if and only if this group is infinite, and this group is not finitely generated if and only if the trace is non-trivial, and the trace is non-trivial if and only if the Jacobi fibration is not trivial. Is trivial. Okay, sorry. So this is for the automorphism group. Now let's turn to the first part. We discuss the B automorphism group, and this is the most important part of this talk. So let me help you recall the definition of this B automorphism group. By definition, this B automorphism group is an image of this F lower sharp homomorphism from E to EX over C to the automorphism of C. It can be also interpreted as this automorphism of sigma in automorphism of C, so that the base change by this sigma of X will isomorphic to X over this C. And from this, we can observe that two fibers of F under the in the same B automorphism orbit will have isomorphic fibers. So if we assume this B automorphism group is infinite, you will find infinite many fibers that are isomorphic. So in particular, the fibration F must be isotrivial. So we will first discuss isotrivial fibrations. Let's first introduce the notion of standard isotrivial fibration. So given a isotrivial surface fibration from X to C with general fiber F, it is called a standard if we can find a finite group scheme G simultaneously acting on F and another smooth projective curve C prime, so that this fibration is birationally equivalent to this fibration. So here you have F cross C prime, and this G acts both on F and C prime, and it acts diagonally on the product, and you have this fibration, this fibration P2 to the C prime over G, and this is isomorphism. These standard fibration like this is called standard isotrivial fibrations. And the standard fibrations are the best form of isotrivial fibrations we can expect. And the fundamental structure theorem for isotrivial fibration over C is like this. So it says that any isotrivial surface fibration over C are automatically isotrivial. So this group, so the structure of isotrivial surface fibration over C is quite simple. And this theorem has many applications. Oh, I should say that this theorem is contained in the Bovis book, Complex Algebraic Surface, and the Policies paper for genus. This case deals with genus 1, and this is genus at least 2. This theorem is very useful in the study of isotrivial surface fibrations over C. In fact, it is used in for example, the so-called Bagniera de Franchis classification, which classifies the so-called hyperelliptic surfaces.
Maybe the result already known to Serrano.
Yes, but I think this book is this result is very early. I think it's not proved by Bovee. It should be earlier than this book, but I didn't find who really proved this theorem. Firstly, okay. Anyway, let's continue. And it is this structural result is also used by Bennett and Miranda for the calculation of the automorphism group of these hyperelliptic surfaces. And policy has applied this structure to calculate many numerical invariants of actual fibrations. And I should also mention that there is the advantage of the standard fibration is that there is another isotrivial fibration. There is another isotrivial fibration. Let's check this picture. So if X is birational to this F cross C prime modulo this G, it will naturally admit another fibration P1 maps to F cross F quotient by G, and the fiber of this P1 will be C prime. The general fiber of this fibration will be C prime, and this will be also useful. And this structural theorem can also help to calculate the equivalent automorphism group and the B automorphism group. And we will see later. And now let's consider case impulsive characteristics. And in fact, if the fiber genus is at least 2, then this result is still true. And we will formulate another version of the theorem, but we will also involve the equivalent automorphism. Okay, so we are going to formulate another version of the theorem 4.1, and which involves the equivalent automorphism group. Here F is a general fiber of this F, and under our setting F is at least genus 2, so its automorphism group is finitely dark. And we know this let U be the smooth locus of F, then this fibration is characterized by the homomorphism from the dark fundamental group to the automorphism group of F. And we can use this M, which represents the isomorphism functor from XU to F cross U over U. And this M admits an action of this gamma by the action of gamma on the second factor, and this becomes an Ida-Galois cover of U. Using this, we can see that XU is canonical isomorphism to the F cross M modulo this gamma. And the fibration is like this. Moreover, this construction M and gamma are both canonical. So the equivalent automorphism group, which is equal to the equivalent automorphism over U. In fact, the action of this group lives on the product on this side. So we can summarize like this. Suppose F X2C is the isotrivial fibration of genus G at least 2, and U is a smooth locus. Then we can find the Ida-Galois cover M with the Galois group gamma equal to the automorphism group of F, and the equivalent automorphism group this time is identified with this group, the total automorphism group of this M over U. And with this M, we can find XU over U is isomorphic to the cross modulo gamma, and fibered over this M cross gamma, which is equal to U. This is another version of theorem 4.1, but we include the equivalent automorphism group, which is now identified with the equivalent torsor automorphism group of a certain torsor naturally associated with this X. Now let's discuss the genus 1 fibrations. So difference between positive characteristic and the characteristic 0 is that theorem 4.1 is not true for genus 1 fibrations. Before I give you the example, I will first tell you what is true, and from this true result, you can see how the original theorem 4.1 is right. It is wrong. So in fact, if you have an isotrivial fibration of genus 1, and E is a smooth general fiber, and U is a smooth locus of F, so in fact, you can also find the finite group scheme G acting faithfully on this E and another G torsor U prime over U, so that still XU over U is isomorphic to the E cross U modulo this G, and GX on the cross diagonally. But this time you can see that this finite group scheme G, G is a subgroup scheme of the automorphism of E. This time, this group scheme is not rigid. It is a semi-direct product with this finite group. So this G is not necessarily EDA, but its identity component is abelian. This is good for us. And the torsor U prime is not necessarily irreducible, and it can also be non-reduced. And with this, we can see that the G action on this U prime, in comparison with the theorem 4.1, the point is that the G action on this U prime does not necessarily extend to its normal compactification, U prime to containing C prime, even if U prime is smooth and irreducible. So even if this U prime is very nice, but this G can be not necessarily that, it can be an infinite small group scheme. And its action on this U prime do not extend to this C prime. So you do not have the theorem 4.1. And as a consequence, in this case, you still have this projection from E cross U prime to G to this E cross G. And by this P1, you will still find the general fiber of this projection will contain U prime as an open subset. But however, the general fiber will not necessarily equal to C prime unless this G action actually extends to G1 to C prime. But usually this is not the case. And then sometimes the G action extends to some non-normal compactification, and this time this fiber will be the general fiber will be singular. So this is the main difference. And in fact, we can actually construct an example. I will briefly describe this example. So the fibration like this X will have a Cagliari dimension 1, and this fibration X is uniruled, and the Jacobi fibration of this F is trivial. But in this case, the smooth locus, okay, I should this should be U prime. U prime is A1. But this fibration, as I mentioned, this fibration has a singular general fiber. So this prevents this X to be a standard type. Now let me sketch the proof of proposition 4.2. And with this, with proposition 4.2, I will introduce the main result. This is the same as proposition 4.2. This is for reminder. It says if you have a isotrivial fibration of genus 1, and you take the smooth locus, then you will find the G torsor, some G acting on this general fiber E and G torsor U prime, so that XU over U is equal to this formulation. And to do this, we need to we observe that the main reason is that the E is not the automorphism group of E is not rigid. So in order to make it rigid, we need to take a rigidification. So we do not consider E itself, but consider the pair E along with degree n divisor which is n times identity. Then the automorphism of this pair will be a finite group scheme. Still, it's not rigid, but it's at least finite. And to do this, we fix an invertible sheaf L on X of relative degrees of some relative degree n. And in fact, more generally, we can just take a rational point C in the relative Picard functor over U. And we take this M to be the isomorphism of this pair XU and L with the trivial case, the E cross U and the trivial degree n divisor. Then this in fact okay, I should say more about this. So this is the functor which maps schema over U Z to the pair of isomorphism from XZ to the E cross Z, along with an isomorphism of L with this group times tensor some pullback divisors, pullback line bundles. And this functor is actually represented by a torsor M over U under some structure group. So this is the proposition 4.2. And this isomorphism is natural, and you just check the Fontorian definition. But we want to relate this this isomorphism with equivalent automorphism group. As I mentioned, in case of genus at least 2, you also have a torsor M under some G. At that time, this M and G are naturally occurred, and so the equivalent automorphism group actually lifts on the lifts to this E cross M to M. But in this time, we our construction our construction depends on the choice of this C or this line bundle or other or this C, they are equivalent. So it is not canonical. To overcome this this question, we find that in fact this equivalent automorphism group can actually act on this group, and under this group, the subgroup NC that stabilizes this C can actually lift to this group. And here I have a lemma. So the stabilizer of C is equal to the E toss of M over this U, and the homomorphism, if lower sharp maps NC to this P automorphism is in fact an equivalence relation. So when you study this, you will have it's equivalent to study this E toss M over U. So let's summarize the case of G equal to 1. When you have an isotrivial fibration of genus G equal to 1 and take U to be smooth locals, you will find the torsor over U on the group G, which is En cross automorphism of E. And this torsor group is in fact a subgroup equivalent to this P automorphism group, and XU is realized as this cross product. And this is, I copied the summary of G at least 2. And you can summarize this 2 cases altogether. So whenever you have a genus 1 fibration, genus at least 1 fibration, and take a fiber F, smooth fiber F, then you will find a group scheme G acting faithfully on F and another G torsor M, so that XU over U is isomorphic to the F cross M modular G fibered over this M over G. And at this time, this B equivalent automorphism group is equivalent to the E torsor automorphism group of M. And the key technical theorem is as follows. I will let me say this theorem. So let U be a smooth curve over K, and G be a finite group scheme over K, and assume its identity component is abelian. Then if a torsor, if you are given a G torsor and this G torsor, this associated E torsor subgroup, equivalent torsor automorphism subgroup is infinite, then this G torsor T will have very nice properties. In fact, it will reduce to a G prime torsor for a smaller subgroup, for a subgroup scheme, G prime torsor T prime under a subgroup scheme G prime, so that this T prime is irreducible and smooth, and the E torsor E T prime over U is equivalent to this group, so it's still infinite. And more importantly, it says that the G prime action on this T prime extend to its normal compactification, say C prime. Here is some remarks. If you have a torsor T over U, and it is called Norrie reduced if it cannot reduce to any strictly smaller torsor. So this is smallest torsors over U that it can never reduce to any smaller one. And every torsor under a finite group scheme of a variety of K admits a unique associated Norrie reduced torsor. So you have a torsor at first, and if it cannot reduce anymore, then it's already Norrie reduced. If it can reduce, then you reduce and reduce and reduce again, and finally you will get a Norrie reduced torsor. If we use a language of Norrie reduced torsor, then then the T prime that T reduces in the above theorem is exactly the Norrie reduced torsor. I should say that in general, without any assumption, for example, without the infiniteness assumption on this B automorphism group, then the Norrie, this is B torsor automorphism group. The Norrie reduced torsor associated for a general torsor is not necessarily reduced. So this theorem is really not trivial. Now we can combine this theorem 4.7 with this proposition 4.6, and we get this main theorem. So we are given a fibration of genus G at least to 1, and assume that its B automorphism group is infinite. Then you will find a finite group scheme G prime acting faithfully on a curve F. This F is the general fiber of this F, and the G torsor T prime torsor T prime over U, so that the T prime is a smooth connected curve. The G prime action on T prime extends to its normal compactification, and this overcomes the problem the problem I mentioned for general fibrations. And moreover, this case the E torsor automorphism group is equivalent to this B torsor. This is X over C. Since the G action extends to this C prime, so you can see that this fibration is actually standard type. So in particular, the fibration F must be standard, and the surface X will admit another rational fibration, this P1 fibration, and the fiber of this X is C prime. So in particular, if this C prime is rational, then X must be birationally ruled. In fact, a complete classification of the torsors we mentioned, the G prime torsor T prime, as mentioned with infinite this E torsor automorphism group is classified. So there are 4 cases. Let me see how many times. There are in fact only four cases. The first is T prime is an elliptic curve, and the second case is P1 and G prime is trivial. And the third case is T prime is GA, and G prime is a subgroup of GA. And the last case is similar, but for GM. Here's a remark. The normal compactification of C prime of T prime in the above classification, you can see that they have the same genus with this original C. And this E torsor automorphism group is either is not finitely generated in any of the above case. So we have this correlate. Suppose F is a fibration of genus at least 1. If it has an infinite this base automorphism group, then the Caldera dimension of X can be determined. So it's minus infinity if the base is P1, and it's 0 if G equal to 1 and the base is elliptic curve, and the Caldera dimension is 2, or is 1 if G is at least 2 and GC is equal to 1. And also we can see that the group Bx over C for fibration is either finite or not finitely generated. In fact, with this complete classification of G prime, T prime, we can give a complete list of surface fibrations with infinite B automorphism group. Here is a list for G equal to 1. I don't think I have time to give you the complete list. I will just go through it quickly. So we have 4 cases. Let U be the smooth locus of F. So U can be elliptic curve P1 or A1 or A1 minus 0. And for each case, we have a list. Okay. Finally, I will discuss some application of this material. I will introduce the notion of bounded finite subgroup and the Jordan property. This is introduced by Popov in 2010. A group gamma is said to have bounded finite subgroups, bounded finite subgroup property if there is a constant depending on this gamma, so that the order of every finite subgroup of gamma is bounded by this B gamma. And a group is said to have the Jordan property if there exists a constant, so that every finite subgroup of gamma, it must contain an abelian subgroup of index at most this bound. And some classical results. So Minkowski proves that GLNQ has bounded finite subgroups. And if K has characteristic 0, then GLNK is Jordan, and the criminal group is Jordan. And Popov proves that the birational group of S is Jordan for all algebraic surface, not birationally isomorphic to P1 cross an elliptic curve. And Mention and Zhang Deqi prove that the automorphism group of X modulo its identity component has a bounded finite subgroup, and the automorphism group of X is automatically Jordan if X is projective. But the impositive characteristics, the situation is not so nice. For example, the GLNK is not Jordan, and in particular, PGLNK is also not Jordan. As a result, the automorphism group of P1 cross another curve will not be Jordan. And in the case of surface, the most difficult part to determine whether the automorphism group of S is Jordan lies in the case of Caldera dimension 1. And it's well known that every Caldera dimension 1 surface admits a fibration, a genus 1 fibration. In fact, the fibration is the Itaka fibration of F. And it is classical that the general fiber of F must be smooth if P is not 2 or 3. And if P equals to 2 or 3, this fibration can be quasi-elliptic. And I said as F is a Itaka fibration, the automorphism of S is equal to the equivalent automorphism group. And by our corollary 4.9, this base automorphism group is finite if F is not quasi-elliptic. And as a result, we can see that this automorphism group is in fact equivalent to the relative automorphism group is in fact equivalent to the automorphism group of S. And the relative automorphism group, as is shown before, that is equivalent to this JC, where J is a Jacobi fibration. So we actually find that this group is equivalent to this group. And this group, however, is also equivalent to the key point of its the trace, the small key point of its trace, and with the quotient to be finitely generated. And in summary, we can prove that if S is the minimal algebraic surface of canonical dimension 1, and if the associated genus 1 fibration is not quasi-elliptic, then the automorphism group of S is a Jordan. And this group has a bounded fine subgroup property if and only if the Jacobi fibration of this mu is not trivial. In fact, recently, I have also some other method to prove that the quasi-elliptic case is also true, in fact. So I will not mention the proof, but the result is like this. Suppose this fibration is quasi-elliptic fibration, and this should be X. If X has Clairaut dimension 1, then the B automorphism group is also finite. And as a result, if S is a minimal algebraic surface of Clairaut dimension 1, and suppose its Itaka fibration is quasi-elliptic, then the automorphism group of S must be finite. Okay, thank you. I think I shall stop here.
Yes, thank you. So, are there any questions? So for your last theorem, so you showed automorphism of S. So are there any results for birational automorphism?
Birational automorphism.
But even in characteristic 0 over C, this is known or is not known?
Yeah, this is known in characteristic. This is known in characteristic 0, and it can be proved easily using the Clairaut's canonical boundary formula. But the canonical boundary formula is not available in possible characteristic, and the formation of the right formulation doesn't give the right way to prove the finiteness of this B automorphism group.
Okay. So if you change the base is always a curve in your talk. So yeah, you never thought about if we change the base to be a surface.
If it has first, this relies on the minimum model. So I'm not sure if there's one problem in high dimensional case. So when you have a fibration, the general fiber may be very wide, even not necessarily reducible. Yeah, even maybe reducible, and this so there will be some other difficulties. So mostly I only consider for surface vibrations, but it should also the same ideas may also work for high dimensionals, but I'm not quite sure.
Okay, thank you. So are there any questions? More questions?